pleasure to have Jakob Hedicke from Université de Montréal, who will speak about orderability and the contact Hofer.
Yeah, thanks, and thanks a lot for inviting me. So I'm presenting a joint work with Egor, which connects two notions from contact geometry. So the first one is orderability, and the second one, Hofer type norm on the contactomorphism group. Yeah, so I will explain both of these notions in a minute. So I guess everybody more or less is familiar with contact geometry, but so we work with closed contact manifolds. So in this talk, M is always a closed contact manifold of dimension 2n plus 1 contact structure. Yeah, which means, so we always assume that Xi is co-orientable, so Xi is the kernel of some one form alpha. But it satisfies this non-integrability condition, so alpha wedge the alpha to the power n. This is a volume form on M. Okay. And yeah, similar to symplectic manifolds, one can look at the group of all diffeomorphisms preserving such a contact structure, which is usually called the contactomorphism group. So I will just, for simplicity, note it by G. So G is the identity component, actually, of the group of diffeomorphisms preserving this contact structure Xi. So it's just a set of all, say, diffeomorphisms of M that preserve this distribution. D phi of psi is equal to Xi. Okay, and which are isotopic to the identity via such contactomorphisms. Yeah. Okay, so a few general things. So in general, this contactomorphism group is way less, I would say, rigid than, for example, symplectomorphisms or Hamiltonian diffeomorphisms. So first of all, one can relatively easily see that they are not volume preserving. Yeah. So general contactomorphism does not preserve this volume form. And one can have a lot of squeezing phenomena. For instance, one can often squeeze Dabou balls into other Dabou balls and make sets smaller somehow. Yeah, then, for instance, this contactomorphism group is presumably simple, so it does not have any non-trivial normal subgroups. And also when it comes to kind of norms, so like yeah, on the on the group of Hamiltonian diffeomorphisms, for example, there's this Hofer norm, which is a very natural kind of invariant conjugation invariant norm on the group of Hamiltonian diffeomorphisms. But in this contact case, all of these norms are known to be discrete. So there are actually no kind of continuous invariant norms. So yeah, kind of makes it a bit harder to study this group of contactomorphisms. But instead, there's another notion which does not really exist like this in the symplectic world, and that's the notion of positivity. Yeah? And the reason is basically this contact distribution, which gives a notion of kind of, yeah, it is co-oriented, so there's like a canonical direction pointing out of the contact distribution, which gives a notion of positivity, which one can consider on this group. Which I think was first introduced by Eliashberg and Porter-Rovich in their paper in 2000. So what's the following? I mean, yeah, it's simpler to look at if we just pick a contact form alpha, but in the end, it doesn't really depend on the choice of this form. So we pick some contact form alpha, which is a one form defining this contact distribution. And yeah, in this case, one can define what it means for a path of contactomorphisms in this contactomorphism group to be positively transverse to this contact distribution. And we just say, so we have this path, let's say t between 0 and 1. We say that this path of contactomorphisms, so this lives in G, is positive or non-negative if its contact Hamiltonian with respect to alpha is positive or non-negative. Yeah, so that's just let's say alpha of well, the contact vector field generated by this path. So I just write d over dt phi t. This is positive or non-negative. Okay. And yeah, this defines a special class of paths in the contactomorphism. And one can study the behavior of such paths. Yeah, that's kind of the goal. So first of all, yeah, in many cases, it gives rise to a certain partial order. So let me define that. Yeah, so this is actually in this original paper of Eliashberg and Orderability from 2000. They defined this relation, yeah, using positive paths. So I mean, one can define it on the contactomorphism group, but it turns out to be actually more natural, and that's also where they first define it on the universal cover of the contactomorphism group. Yeah. So we define this relation on G tilde, yeah. So the universal cover, which is, I mean, universal cover just consists of homotopy classes of paths starting at the identity, yeah. Just by, so first of all, one can say that some element in the universal cover is smaller than the identity. Yeah, if and only if. So remember, this is the homotopy class of paths in the contactomorphism group. So it's positive if and only if there exists a path in this homotopy class which is non-negative, yeah, or positive. So let's say there exists some phi t in this homotopy class, which is non-negative. And it's not too hard to see that this kind of relation here is conjugation invariant. So one can use it to define a bi-invariant relation on G tilde. Yeah, so just by saying, let's say we have phi, or let me denote them by tilde maybe to make it clear that this is in the universal cover. Okay, so phi tilde is smaller or equal to psi tilde if and only if identity is smaller or equal to phi tilde inverse of psi tilde. Okay. So this defines a relation on G tilde, which kind of turns out to be quite connected to the rigidity of contactomorphisms in many ways. And one of the basic questions is, when is this relation actually a partial order? Yeah. So that's the definition of orderable given in this Eliashberg-Orderability paper. So we call the contact manifold MSI orderable if this relation is a partial order. Okay. And yeah, so maybe a few examples. So this kind of question, when a contact structure is orderable or not, turns out to be very non-trivial and often requires kind of hard techniques from symplectic topology. And it also seems to be very connected to the rigidity of contactomorphisms. So for instance, if this is a partial order, in most cases where one can show this is a partial order, for instance, it's known that the Sandon conjecture holds, so that any contactomorphism admits a translated point. And it's also connected to certain non-squeezing phenomena, for instance, in pre-quantization spaces. Okay, so first examples. So I think the maybe first example, or one of the first examples that Eliashberg and Orderability gave, at least in some special cases, is the one of cotangent bundles, spherical cotangent bundles of smooth manifolds. Yeah, so we just consider, so I denoted by ST star sigma with its standard contact structure, which is basically, so you take the cotangent bundle of some smooth manifold sigma, let's say without the zero section, and quotient by just the action of the Liouville flow, right? So let's say this positive R action, which is just scaling in the fibers. And the contact structure is in this case induced by the kernel of the standard Liouville form on this, the cotangent quotient also by this action, which is well defined in this case. And it's known that, so I think Eliashberg and Porter-Roberts showed it in some cases. So for instance, whenever, if I'm not wrong, sigma admits a non-vanishing one form. And then later it was shown by other people, I think first maybe by Chernoff and Nemirovsky, that this holds for any manifold. So this is always orderable. Meaning this is a partial order. By the way, I forgot to mention. So there's a nice criterion what orderability actually means. You don't want to kind of consider these partial orders, which are a bit abstract maybe. So it's shown by Eliashberg and Porter-Roberts that this is equivalent to the non-existence of a positive contractible loop of contactomorphisms. So a contact manifold is orderable if and only if there are no positive loops which are contractible. In G, so in the contactomorphism. So basically just like such a path phi t, which forms a closed loop, which is positive and which is contractible in G, in the contactomorphism group. Okay, so kind of in this cotangent bundle case, such loops never exist. Maybe some other examples. So I mean, some non-fillable examples would be, so the first one they also gave in EP, it's just RP 2n plus 1, again with its standard contact structure, which is basically the one that you get as a pre-quantization bundle over, I think, CPN, probably in this case. So this is orderable. And later this result was extended, I think by Granja and Sandon, maybe, and someone else, I forgot, to more general lens spaces. So let's say lens spaces LP with also the standard tight contact structure, which lifts to the tight contact structure on the sphere. They also are. And maybe a last example would be anything that is hypertight. Hypertight just means there exists a contact form without any contractible Reb orbit. Okay, so for a long time, actually, I think there was not really an example of something which is not orderable. And then, so the first and until now only class of examples was constructed in a paper by Eliashberg, Kim, and Porter-Roberts. And it works the following. So we can just consider Liouville manifolds. So let's say W lambda is Liouville. Which just means that d lambda is a symplectic form. And we also require kind of that the Liouville vector field is complete. So there exists a complete vector field Z, let's say. Such that at least if we plug it into d lambda, this gives us back the Liouville form. So it's a Liouville vector field for this Liouville form. And also, that it's kind of a finite type in a certain way. So namely, we want that, well, it basically looks like this. So we want that the Liouville manifold at infinity looks like the symplectization of some closed contact manifold. So basically what it means is there exists some compact subset, so we just draw it. Let's say, okay, so we have some compact region which might have some topology, which is contained, so this is some subset U, which kind of has a smooth boundary. Yeah? This boundary of U is smooth. And so the boundary is transverse to the Liouville flow. So kind of this vector field Z is transverse to the boundary of U. And the kind of the subset U covers the whole manifold if we flow it with the Liouville flow. Yeah, so we kind of have something like W is equal to this is the flow of this Liouville vector field Z of U. Yeah, or in other words, kind of outside of this compact subset U, let's say, this Liouville manifold just looks like the symplectization of boundary of U. Yeah. So in particular, yeah, I mean, I will usually denote it by boundary at infinity, which is kind of the quotient of this region at infinity by the Liouville flow. This looks like, or this is diffeomorphic to the boundary of U, and has a canonical contact structure, which is the quotient of the kernel of this Liouville form by the Liouville flow. Yeah. Yeah, so this is kind of contactomorphic. I mean, this is basically the same construction like with this spherical cotangent bundle, just in a bit more general setting. So this is contactomorphic to boundary of U, and together with the kernel of this Liouville form lambda. Okay. In any case, so they considered such Liouville manifolds, and in this case, one can construct actually non-orderable contact manifolds, namely by looking at stabilizations of such Liouville manifolds. And what they did is, so this is the example of Eliashberg, Kim, and Polterovich, I think from 2009, probably. Yeah, so if you look at the two stabilization, such a Liouville manifold, which just means you take basically W times C2, yeah? Together with, so this gets a new Liouville structure just by looking at the sum of lambda and the canonical form on C2. We just write lambda C2. So this is again a Liouville manifold whose kind of boundary at infinity is a closed contact manifold, right? And so what they showed is that the ideal boundary of this two stabilization, of any two stabilization, is always non-orderable. So it has a contractible positive loop of contactomorphisms. Yeah, let me just write boundary at infinity of Xi, boundary at infinity of W times C2. So this is non-orderable. Okay, and maybe the simplest example of this kind, of course, is if you take W to be just R2n, right? And then R2n times C2 is again R2n plus 2. And its ideal contact boundary is just the standard contact structure on the sphere. So in this case, yeah, let's say some example. So we look at the boundary at infinity of let's say R2n times C2. So this is R2n plus 4, I guess. So this is contactomorphic to the standard S. N plus 3. I hope I did it correctly. Yeah, so any of these contact spheres is always non-orderable. By the way, this holds also for, in this case, for the case n equal to 0, so for S3. Now they also explicitly construct this contractible loop on S3. Yeah. Yeah, maybe on S3, the interesting thing is also, I mean, kind of the standard contact form that one can consider on the contact sphere has this periodic rate flow, right? So it's kind of just the Hopf vibration. And actually this, I mean, one could wonder if this loop, this kind of rate flow is obviously positive, if this is contractible, but it's actually never contractible. And it's quite hard, so they do it in this paper explicitly to construct this positive but contractible loop of contactomorphisms. Yeah. Okay, so this brings me to the main result that we found with Egor. Namely, we kind of generalized this result of Eliashberg, Kim, and Polterovich to the case of one stabilizations. Maybe one thing. So we kind of need one restriction. So we always assume that W is Weinstein, yeah, which is kind of a bit stronger than Liouville. And so basically, what we require is that this Liouville vector field additionally is gradient-like for some Morse function. And we also want that it's of finite type in the sense that this Morse function only has finitely many critical points. Yeah? Basically, what we want is that the skeleton of this Weinstein manifold is nicely behaved in a certain way. Okay, so if we have such a Weinstein manifold, then we can upgrade this result of EKP. So this is the main result of our paper. Yeah, so if we look at one stabilizations for, let's say, n larger equal to 2, if we look at the one stabilization of a Weinstein manifold of dimension 2n, then this is non-orderable. And second, so for the case n equal to 1, we were not able to show this result in full generality. I mean, we still kind of believe that this should be true. But with kind of a different technique than we used to prove this result, we can also show it for this open case of S2 times S1, which is actually the one mentioned in this paper of EKP. Yeah, so for this n equal to 1, we can prove it for S2 times S1, which is actually the it's also kind of the boundary of a one stabilization, namely of P star S1 times C. This is also non-orderable. Okay. And for the rest of the time, I will say a couple of words about the proof.
Sorry, I probably missed that. Why EKP doesn't work for one stabilization?
You mean their construction, or? That is a good question. I mean, they construct this positive loop by hand, I think, on actually for S3. So I mean, S3 is the ideal contact boundary of C2, right? And then they use this loop that they construct on S3 to kind of extend it to any two stabilization in the sense like W times C2. And I think they really need this loop on S3, this positive contractible loop. But yeah, so they cannot do it on W times C somehow with this construction. Maybe I can continue here. Okay, so about the proof. Oh, sorry, yeah.
Is this an exhaustive list of all the non-orderable contact manifolds that are like well known?
Yes,
So-
yes, I think so. So like this Yeah, I mean, exactly. So this EKP is two stabilizations for any Liouville manifold, and then our examples. Yeah, I think. I mean, we have some other criteria to show non-orderability, but we cannot really show that they produce results which are not, or examples which are not one of those yet.
Thank you.
Particular is known for like over twisted.
No. Yeah. This is a very open question. I think. I mean, it's believed to be they are believed to be non-orderable, but I don't think there's any kind of idea yet how to show this. So kind of the techniques that we use also, for some reason, they over twisted manifolds resist them completely. Like they don't work. Yeah. Yeah. So the proof. So basically, I mean, the proof consists of two main ingredients, I would say, and one of them, as the title says, is this contact Hofer norm. So yeah, I'll first introduce this one. And yeah, as I said, so in general, it's very hard to find meaningful and especially invariant norms on the contactomorphism group. But one can actually do a similar approach like for Hamiltonian symplectomorphisms in the contact world that was done by Egor in his work. It's just not invariant, yeah. But one still gets something meaningful. So in some sense, let me write it down. I mean, the kind of ansatz is very similar to the symplectic case. So we consider a path of contactomorphisms, let's say between 0 and 1. And given such a path, of course, it defines a contact Hamiltonian, right? Just plugging it into the contact form. And using this contact Hamiltonian, we can define the length of this path. So just, let's say, denoted by L alpha of phi t can be defined as, let's say, integral from 0 to 1. And then we look at the maximum norm of its contact Hamiltonian. So alpha, let's say absolute value. So alpha of phi t or dt. So this defines kind of a length, which of course heavily depends on this alpha. Yeah. But still, yeah, one gets a norm out of it just by looking at the infimum of all such lengths. So if we have a given contactomorphism, let's say phi in G in the contactomorphism group, we can define its contact Hofer norm just by looking at the infimum over all these lengths, right? So we look at infimum, let's say phi t, such that phi of 1 is equal to phi, and then we look at L alpha of phi t. Okay, and it's kind of a result of Egor, as I said, that this indeed defines a norm. From 2014, maybe, or 2017. I don't know when it was published. Yeah, 17. Yeah, so this is actually a norm on G. And by that I mean it satisfies triangular inequality with respect to composition. It's compatible with taking the inverse. It's non-degenerate, in particular on G, although this we actually will not really use for the proof. And well, it's not invariant, but it satisfies this property that we will heavily use, which is kind of called naturality. So it's natural with respect to conjugation in the sense that, let's say, we conjugate some element phi and take the contact Hofer norm with respect to a contact form alpha, then this gives us the contact Hofer norm of phi with respect to the pullback of alpha, with respect to this contactomorphism psi. That's phi of psi pullback alpha. Okay. And well, kind of in our situation, we work on the universal cover, and indeed it's the case that this extends to pseudo norm on the universal cover. So This extends to a pseudonorm or lifts to a pseudonorm. On G tilde, right? So just basically if we have a homotopy class of paths in the universal cover, we just look at or take the infimum over all paths of this length in this given homotopy class instead of over all paths. Yeah. However, on the universal cover, it's in general not known if this is a norm. I don't know if I guess there are some cases where it's known, but in general, this is still open if this is an actual norm on the universal cover or not. Okay.
But what is the expectation of this?
I guess yes. I mean, Egor is the expert, but I think it's known for some pre-quantization spaces that it is. And I would expect that it is always probably right, but.
I would say the expectation is that it is, but exactly like in the symplectic case, you know, we expect it, but we cannot prove it. In general, of course.
Okay, so now the question, of course, is how is this related to orderability? And so, yeah, maybe I should say, so this norm, of course, depends on the contact form alpha, but it seems that its global properties, like for instance, boundedness or also the topology induced by this norm, they do not really depend on alpha. So they are kind of more invariant quantities. And so to connect this to orderability, so this is basically follows from a result of my PhD thesis from 21. Namely, one can show that if M psi is orderable, then this norm is always unbounded along the lift of the rate flow of this contact form, which is actually not too hard to show. So this is unbounded along, let me just denote the lift of the rate flow at time t by phi t alpha tilde. Yeah, so this is in G tilde. So it's the lift of this rate path at fixed time t. Yeah, one can write this down explicitly. Even I mean, so this contact Hofer norm of this path at time t is precisely the absolute value of t. So in the sense that the rate flow of alpha defines a geodesic. So this contact Hofer norm in the orderable case. Okay. And well, it seems that this one can use this kind of observation to have some implicit criterion for this non-orderability, right? So the kind of the goal is, and that's how we show non-orderability, is to bound the contact Hofer norm along the rate flow. So the goal, when we kind of shorten this rate path, so let's say phi t alpha, where t is in between 0 and capital T. So just the rate path in the contactomorphism group inside its homotopy class, which is phi t alpha tilde. Yeah, and in particular, bound the contact Hofer norm along this rate flow, independent of t. Yeah. Okay, and yeah, so the main tool that we use to do this is kind of a well-known tool in contact topology, I would say, namely it's supporting open book decompositions. And let me just briefly say what they are. So an open book decomposition is kind of in general a way to decompose a contact manifold into kind of like vibration of symplectic codimension 1 submanifolds, yeah, which are often easier to treat. So an open book decomposition k theta. So we call this an open book supporting a given context structure. Let's say m psi. And this basically consists of, so first of all, what is this k? So this k, which is usually called binding, this is a codimension 2 contact submanifold of our M, 2n minus 1, I guess, inside M 2n plus 1. So this is a codimension 2 contact submanifold. And this theta is a fibration of the complement over S1. So theta goes from the complement of the binding onto S1. Yeah, so this vibration such that so in this contact case we require this kind of extra condition that if we pick a contact form, let's say which is sufficiently nice, then it restricts to a symplectic form on the pages, meaning the fibers over S1. Yeah, so such that this contact form d alpha is symplectic. So in particular, the pages kind of get the structure of Liouville domains, right? With this contact form. On the pages. So theta, let's say the pre-image of S for all S in S1. And then additionally, one usually requires some technical conditions. Yeah, let me skip them, but basically they say that this K has a certain kind of certain neighborhood in which the contact structure has a normal form, and that all the orientations that you have match kind of well together. Yeah, in any case, so there's kind of an important result by Giroux, which one can use in contact topology, which states that indeed any contact structure is always supported by an open book with Weinstein pages. Yeah. And this is what we are going to use. Actually, I mean, we are not really using his results in some sense, but we work with explicit open book decompositions. An open book such that the pages, if you pick, well, there's if you pick a certain form, which is called an ideal Giroux form, which let's say up to a small perturbation always exists, then the pages turn into Weinstein manifolds. Let me just write with Weinstein pages. Okay. And now the example, and actually I think it's basically the only example that we will need to prove at least our main result. Is the following. Yeah, namely, if you look at the one stabilization, this always has kind of a canonical open book. Yeah. So just let's say we have our Weinstein manifold. then the ideal contact boundary of the one stabilization has kind of a canonical open book. Whose pages are exact symplectomorphic to W itself. And yeah, basically, I think the way to construct it is as follows. So remember this ideal contact boundary is contactomorphic to basically the boundary of, if we take some let's say smooth star-shaped domain with smooth boundary inside W times C, right? Let me just denote it by U. Right, so W times C. This is contactomorphic to, let's say we take this domain with smooth boundaries, so it's contactomorphic to boundary of U, and then kernel of the Liouville form on W times C, right, which was basically lambda on W plus the Liouville form on C. And on this guy, one can get an open book just by, I mean, kind of, this is a subset of this product W times C. And we can basically look at the projection, the pre-image of 0 in the second coordinate, right? So basically our K, we can define to be all the points, let's say, EZ in boundary of U, such that Z is equal to 0. Yeah, so this defines the codimension 2 contact submanifold, and then this vibration, so this theta just becomes projection onto well, basically the angular coordinate in C, right? If you kind of go around the origin. Okay. And yeah, so the first lemma, which is kind of the key lemma to bound the contact Hofer norm in general, uses precisely such open book decompositions in the following way. Yeah, first, yeah, let me write it down. Or no, maybe, I mean, given such a Weinstein manifold, of course, there's a preferred submanifold, which is called the skeleton, right? I mean, probably everybody knows. So the skeleton of W is just basically the subset on which everything contracts if you flow backwards with a Liouville flow, right? So this is, I mean, if we use this U, and then this would be just, let's say, the intersection T smaller equal to 0, and then you just flow backwards with a Liouville flow, so phi T C of, let's say, the closure of U, right? So it's kind of, let's say if we have this picture, and this is our Liouville flow, then at some point, if we flow backwards, everything yeah, contracts onto the skeleton, which kind of maybe looks like this. So it would be, I guess in this case, it would be something like these two circles. So the skeleton is always in this, at least in this Weinstein case, which we are considering, is always like a, I mean, kind of an isotropic complex in some sense. So it's not really a manifold, but it's kind of a manifold up to, let's say, if we take out some lower dimensional subset, right? So it's kind of like, yeah, looks a bit like a CW complex in a sense, right? And all its pieces are actually isotropic. I mean, it consists of isotropic submanifolds, right? So what do I want to say? Ah, yeah. So the lemma, the main lemma is the following, namely, we look at the complement of such a skeleton inside the contact manifold of a page. Yeah, so let's say we have an open book decomposition. and it has a page W. With skeleton, let's say L. So the skeleton again is with respect to some ideal Giroux form. Then actually we can show that the contact Hofer norm is bounded on the complement of the skeleton. So if we look at contactomorphisms which are compactly supported in the complement of the skeleton. So let's say this, the contact Hofer norm is bounded, so universally bounded on, let me just denote it by G and then sub C. So it's compactly supported paths of contactomorphisms which are compactly supported in the complement of the skeleton L. So let's say we take M without L. And we look at, so the universal cover, so paths which are compactly supported in M set minus L. Okay. And in this case, this contact Hofer norm is bounded on these contactomorphisms. So basically, I mean, if you consider it as a subset of universal cover of the contactomorphism group of M, whenever we have a path of contactomorphisms which is compactly supported in the complement of L, then its contact Hofer norm is bounded by some universal constant. Okay, and the basic idea is basically following. I mean, what we use, so what is so special about the skeletons is, yeah, try to draw. Sure. So it's basically the existence of the following map. So if we have this open decomposition, and let's say we have here a page, this page W, and the skeleton, then actually, so whenever we pick a second page, which is disjoint from W, let's say W prime, which also has a skeleton. Yeah, so let's say this is L and this is L prime. So the interesting thing about these open books is that in this case, actually there exists a kind of a contraction which contracts everything in the complement of L onto an arbitrarily small neighborhood of L prime. Yeah? And well, its contact Hamiltonian is basically given, so if we look outside of the binding, it's well defined, basically given by the sign of theta, yeah, where theta is kind of this open book decomposition. So this defines kind of a contact flow, and the contact flow does basically the following. So it kind of contracts everything, yeah, in the complement of this L onto an arbitrarily small neighborhood of L prime. Yeah, and let's say if you're in the page, it kind of, so on the page W, it's just given by the Liouville flow, and on W prime by the inverse Liouville flow. Yeah, so it kind of flows into the binding, crosses the binding, and then flows here into the skeleton. I hope it gets more or less clear from the picture. But
Sorry, I'm a little confused. It's a complement of a skeleton of one page or the union of all?
So the complement of the skeleton is the whole manifold except this part here, except L.
L is like the skeleton of one page.
Yeah, L is the skeleton of one page.
So that's the complement of one page.
No, it's not the complement of the whole page, but it's just the complement of this one skeleton, which lies inside the page.
Skeleton of one page. The picture looks like you.
I mean, the picture is just, I'm not very good at drawing, but so this is one page, right? And here is the binding, and then here is another page. And kind of, this is like the S1. I mean,
L is removed, not L prime.
No, just L is removed, yes.
Okay.
Yeah. So just L is removed, but this L prime you need because you want this flow that everything contracts onto a different skeleton. But I could kind of choose a different page. Let's say I could choose a page here. yeah, with some other skeleton L prime prime, and then I would have a different flow that contracts everything from a neighborhood of an arbitrarily small, which contracts every neighborhood in the complement of L into an arbitrarily small neighborhood of L prime prime. So it does not really depend on the second page that you choose, but you always get this kind of flow. And what this flow does is basically it kind of, if you take something which is compactly supported in the complement of L, then it shortens the contact Hofer norm, because it's, if you remember this, I erased it, but if you remember this formula, that if you conjugate with something with respect to alpha, then this becomes contact Hofer norm of the pullback of alpha with respect to psi. And this kind of contraction has the property that it moves the support of, so let's say something is compactly supported outside of L, right? Like here. It moves the support very close to L prime. And then next to L prime, the kind of scaling factor that you get from taking this pullback becomes very small, let's say. And if the scaling factor is very small, then also this contact Hofer norm becomes very small. So you kind of use this naturality condition.
Okay. How do you know the scaling factor is small?
That's just a property of this. I mean, the scaling factor is very small next to L prime, but it's very large, of course, than if you are next to L. Yeah, but we kind of move the support of something given close to L prime. And then it's in a region, supported in a region where the scaling factor is very small. That's kind of the idea.
And what happened to the binding again? What did you say?
Say again?
Then what happened to the binding? You also flow that too?
No, the binding, the binding doesn't move. Yeah. I mean, the flow kind of, the flow of the contact vector field in finite time crosses the binding, and then it enters this page, basically, W prime. I mean, it kind of, yeah, I think it's very similar to this kind of standard contraction that people consider on R2n+1, right? Which just contracts up to n+1 into the origin, which is given by, let's say, e to the minus tx, e to the minus ty, and then e to the minus 2tz.
Yeah, but
If you have this
that one,
limits.
the scaling factor is large. This,
No, then the scaling factor is e to the minus 2t, right? Or e to the minus t. If you look at the scaling factor of this one. But of course, this is a closed contact manifold. So in total, the scaling factor has to integrate to 1. Just the point is that we kind of, the scaling factor is large outside of the support of our compactly supported guide that we look at. Yeah. Okay, but let me say a bit about the rest of the proof. I guess I have 5 minutes left. So the second kind of ingredient, which is very simple, actually. So of course, the Reb flow in general is not, the Reb flow is never supported in the complement of a skeleton, right? It's always supported in the whole manifold. So we need something to apply this lemma to kind of bound the contact Hofer norm. And what we do is we use some fragmentation result. And this is actually very simple. So, namely, whenever you have a compact subset of your contact manifold, and let's say you have a path of contactomorphisms, so this is in G, such that the image of K minus never touches K plus under this path. So Ft of K minus intersected with K plus is empty. Then what you can do is you can basically cut out the contact Hamiltonian, like cut the contact Hamiltonian away from the image of K minus and get two, write Ft as a composition of two contactomorphisms which are compactly supported in the complements of K plus and minus. Yeah, so if this is the case, then you can write Ft as a composition ft plus composed with ft minus where the support of ft plus minus lies in M without k plus minus. Okay. So in kind of in our case, what we want to do is this k plus minus we want it to be two skeleton of pages of an open book, and our f we want to do this with the rate flow, right? So we kind of in some sense want to achieve that the image of a skeleton under the rate flow does never touch another given skeleton of some page. And in general, of course, it does. So one has to perturb the rate flow in a kind of clever way. And that's kind of the a bit tricky part. Yeah, so just remember, so this ideal boundary of W times C. So this has an open book with whose pages are exact symplectomorphic to W, right? Which was basically this open book in this example. And now we can pick two pages. Let's say W plus and W minus, which are kind of two disjoint pages of this open book. And they have two skeletons. And what we want to achieve is that kind of by a small perturbation, the rate flow, like by a Hofer small perturbation, the rate flow, the image of L plus under the rate flow does never touch L minus. Because in this case, if this is the case, we can apply first this fragmentation lemma to write it as a composition of, one F, which is compactly supported in, let's say, the complement of L plus, and another F, which is compactly supported in the complement of L minus, and then apply this lemma 1, right? Which says that whenever we're in the complement of a fixed skeleton, then this contact Hofer norm is bounded. Yeah. Okay, so we have these two skeletons. And okay, the first case is relatively easy, namely if W is subcritical. Yeah, so let's say W is subcritical, which means basically that, so remember the skeleton kind of consists of pieces which are smooth manifolds, and the highest dimension such a smooth manifold can have is n minus 1 in the subcritical case. And that kind of means that that basically by a small perturbation, generically the image of one of these skeletons is avoiding the other skeleton. So we can kind of do a Hofer small perturbation. Let's say up to Hofer small perturbation in the subcritical case. The image of L plus, or let's say, L minus, L plus doesn't matter, under the rate flow avoids L minus. Yeah, so intersected with L minus is empty set. Okay. Right, and in this case, I mean, in this kind of subcritical case, up to this Hofer small perturbation, we can achieve that we can apply this lemma 2. So we can fragment the rate flow into these two kind of paths, which are compactly supported in complements of skeleta, and then, I mean, that's important. complements of these two fixed skeleta. So I fix these two skeleta, and then it's kind of supported in the complement of these two fixed skeleta. And we can apply lemma 1. So the rib flow is just bounded, and hence the contact manifold is non-orderable. Yeah. And okay, so yeah, the tricky part is, I guess my time is up, but just maybe a few words. So the case if W is critical, that's a bit more tricky, and that's where we kind of need this dimension condition also. Because in this case, it turns out that if you have this particular situation, that you kind of have this open book of one stabilization. So in this case, kind of the monodromy of the open book is just isotopic to the identity. So it's like the trivial monodromy. And it turns out that in this case, the skeleton, if you look at it inside the contact manifold, the critical part of it is always a Legendre submanifold, and the submanifold is known to be loose. So it's a loose Legendre, say L plus, or let me write L plus crit. So it's like those parts of this kind of isotropic complex, which are n-dimensional submanifolds of M, and they form a loose Legendre inside this contact manifold. This loose Legendre, I mean, I will not maybe go into detail what this means, but that's kind of a technical condition for a Legendre submanifold such that you can apply an H principle due to Murphy. So this is a loose inside this contact manifold M psi. And of course L minus 2, so L minus plus are both loose. So this is a result of Casals and Presas. And okay, just one sentence. So in this loose case, whenever the skeleton is loose, and the rib flow looks kind of nice, like in this one stabilization case, one can apply a result of Nakamura, which basically bounds the contact Hofer norm along paths of loose Legendres. And using this result of Nakamura, one can compose the rib flow with kind of a path that ensures that the image of the skeleton, let's say L plus, always stays close to L plus, yeah, arbitrarily close, and which is uniformly bounded, independent of T. And then use this, I mean, together with the properties of the contact Hofer norm, like triangular inequality and so on, to finally bound the contact Hofer norm of the rib flow, also in this case. Yeah? Okay, yeah, so I think my time is up. So if there are any questions.
Okay.
Thanks, yeah.
Let's see. Yeah, so this open book is really just to give you a way to construct this contact the flow. So
Yes. Yes.
So let's say you start with like an over twisted contact open book, then it's just maybe it's not as easy to construct this flow. But once you construct this flow mapping one of the page to the maybe it's a compactly supported skeleton of the other, sorry, a skeleton of the other, then.
Well, so this flow actually exists for any open book. Yeah, it doesn't really matter, and also this lemma 1 holds for any contact manifold, also over twisted ones, for the complement of skeleta. The kind of the difficult part is this one in the over twisted case. So it seems that and actually one can show this, that over twisted contact manifolds never have a subcritical skeleton. And it also does not seem to be like the skeleton does also not seem to be loose somehow. So we cannot really apply any of these techniques to perturb the rate flow and make it somehow avoid the skeleton in some sense. So this yeah, just doesn't seem to work.
But you expect it to be true, or maybe it's just not true?
At the moment, I don't know at all anymore. I mean, I think people believed it to be true. I mean, so over-twisted manifolds are non-orderable in some weaker senses. I don't know if you heard about this. So there are two different other kind of partial orders. So one of them uses contact non-squeezing. And the other one is basically you look at the contact product, which is like m times r, I guess, which is again a contact manifold, and then you can like any contactomorphism defines a Legendre in this contact manifold, right? And if you look at so you can define non-orderability also by looking at positive paths of Legendrians inside this contact product. And if you do this for over-twisted contact manifolds, they turn out to be non-orderable in this kind of Legendrian sense in the contact product. But it's known to be, I mean, it's not known if this notion of orderability coincides with this one using positive paths. It's just known to be weaker, kind of. And I mean, there are actually some results by I think also Casals and Presas, which construct positive loops on over-twisted free manifolds. But it seems to be impossible to show if they are contractible or not. So this is not known. Yeah, but it seems to be kind of open.